Today we want to start off with something familiar that we can connect to the new thing that we're looking at. So let's take a quick trip in the Wayback Machine to linear functions and how linear functions work. In particular, viewing linear functions numerically and a couple of different ways to express a linear function in an equation. And then once we remind ourselves of how this works in 2 variables, we can upgrade this to be in 3 variables. So let's go. So here are 2 equations of the lines. I've given you 2 points, and here are 2 ways we can write the equation of a line. We know what we need for a line is a point and a slope. And we know that the slope represents how y is changing with respect to x. So the coefficient of the x in the linear equation is how y is changing with respect to x. Notice that's in this slope-intercept form or in the point-slope form. So the slope m is, we usually say, the rise over the run. What we're talking about is the change in y with respect to x, how y is changing with respect to x. So when we see that in this pair of points that y goes from 3 to 7, so that the delta y is a positive 4. And while that's happening, x goes from -1 to 1, so the delta x is a positive 2. So slope is 4 over 2, which is 2. The slope represents a ratio, so I can simplify the ratio to express the slope. Now all we need is one of the points, x naught, y naught, and we have the slope, and we can write the equation of the line. So I'm going to pick one of these points. I'll start with -1, 3. And I'll put in the point. So y starts off at 3 and increases by 2 whenever x increases by 1. And we're starting off at -1. So I'm going to write x minus a -1. Oh, but the points are in blue, not red. Messed up the colors, messed up the whole semester. In my experience, once I've done that, everybody flunks. So we might as well just stop now. Well, I'm kidding. Only half of you flunk when I make this mistake in the beginning of the semester. Now, some of you are really concerned with what's going on at 0. And so you're going to want to write your equation in slope-intercept form. And some of you, weirdly, are going to want to know which direction to go before you know where to start. So you're going to write y equals mx plus b instead of b plus mx. That's weird, but you do you. So what we can do here to solve for the b is just plug in one of the points and figure out what the b is. So you can take any one of these points, say y is 3 and x is -1. And x gets multiplied by the slope 2. And then so y is equal to b plus m times x. And this tells us that b is equal to 5. So we can write our equation, y is equal to 5 plus 2x. There's nothing in particular that's special about the point -1, 3. It's just the first point that I wrote down. But I could have just easily used the point 1, 7 and written y is equal to 7 plus 2 times x minus a regular 1. The main thing that we want to notice here is the structure. We start off with a number indicating where y begins, and then we write the +2 is what's happening to y. So in this equation, the y starts off at 7 when x is 1, when there's no change. So this point is saying y is 7 And the +2 is telling us that y increases by 2. We're including the sign in this as well. So this +2 part says y increases by 2. Every unit. So this linear function will have this pattern of repeated addition. We're adding 2 a bunch of times, and that's why we can summarize with multiplication, 2 times the quantity x minus 1. X minus 1 is the number of times we add 2. That's how we want to think about linear functions. X minus 1 is counting the number of times we add 2. Addition is repeated multiplication. If we want to see this play out in a table of values that extends beyond the 2 that we were given, we have the point -1, 3 and the point 1, 7. We have figured out the point 0, 5 goes in the middle because that's where we found this. We can think about y starting off at 5 when x is equal to 0, but y is still increasing by 2 whenever x increases by 1. So we can figure out more points. We have the 0, 5. After 1, 7 will be 2, 9. Before -1, 3 will be -2, 1. And we see how y is changing, always the same. Increasing by 2 whenever x increases by 1. That's what's making a linear function. That's how y is changing with respect to x. Let's look at another example in a table. Let's look at the value of z as it changes with respect to y and with respect to x. So now I'm looking at the table I picked and I'm wondering why I picked such strange numbers, but that's okay. I didn't give myself enough space. So now let's consider another example where we have a table of values. And I'm going to put x in a column going down this way. So I'm going to have x values go 2, 4, 6, 8. And I'm going to have, let's go 10. I want 5 of them. And I'm going to have, these are all x. And let's have y change across the column. So y's will go just count 1, 2, 3, 4. So y's will count 1, 2, 3, 4, 5. And these will be all the y values. So now our table of values, instead of just being x and y, is going to have z as a function of y. Instead of having a table of values where y is a function of x, we'll have a table of values where z is a function of x and y. So let's see, let's say we got 85, and then 130, and then next would be 175, and then 220. And let's go down the table this way. After 85, we have going down, we have 125, and then 165, and then 205. I haven't given you all the values in the table because we're going to fill this out ourselves. And what we're going to do is we're going to say that z is a function of x and y, and z is linear. So in the table of values are the values of z. And so we're seeing that z of 2, 1 is 85. So that's what that point will mean. So here's the point. So this entry in the box, that means that f of 2, 1 is equal to 85. Z is equal to 85 when x is 2 and y is 1. Notice that we have to have x equals 2 and y equals 1. We have two inputs. It would be unreasonable for me to say, what is the value of z when x is equal to 10? That's not enough information. That's like saying my address is 3300. You need two coordinates to make an address. So take a moment and think about what the rest of the table should be. Remember that z is a linear function. Linear functions have a constant rate of change. We have two different directions, an x direction and a y direction. So we're going to need two different rates of change. So what is the value of z when x is 2 and y is 5? So what's going on up here? You go ahead and type your answer in the chat.
255.
255 or 265 or 235? Seems like most of the chat is saying 265. So democracy wins. I'm just kidding. It doesn't matter what everybody votes. You might all vote wrong. So 265, and I also see in the chat how we come up with this value. We go from 85 to 130 to 175 to 220 to 265. So we can see that z is increasing by 45 whenever y increases by 1. So to figure out this value, this value means that f of 2,5 is equal to 265. And the way that we can determine that is that z is increasing by 45 when y increases by 1. We're looking at the constant rate of change going across this row. This is what's happening when x is equal to 2. So if I go down to the next place where x is equal to 4, what should my entries be? Let's figure out what this row should be following this rule. Z is linear in the x direction and the y direction. So if we, instead of starting at 85, we start off at 125, what should be f of 4, 2? What are we going to put for f of 4, 2? Following this same rule, we'll see that f of 4, 2, we're going to increase by 45, and 25 and 45 is 160, 10. We'll take the 125 and add 45. Because z increases by 45 when y increases by 1. And then we can just follow that out for the rest of that row. So 170 plus 45 is 215. And then we'll have 260. And then we'll have 305. We're just following the pattern that Z increases by 45 when Y increases by 1. Any questions? Now let's consider what's going on in the other direction. Let's take a minute and find, not a whole minute, let's take a moment and I'm gonna have to look up how long a unit of time a moment is. That's gonna bug me the rest of the day. So in the X direction, if we just take all this information that we have when Y is equal to 1, we can use that to figure out what's going on when Y is 1 and X is 10. So if we want to find F of 10, 1, we go from 85 to 125 to 165 to 205. So here at 10, 1, we must be at 245. That's what the chat all agrees. And we can say we can figure this out by saying Z is increasing by 40 when X increases by 2. Notice that X is increasing by a different amount. So Z increases by 40 when X increases by 2. So now we can see we're just describing the rate of change of Z with respect to X. And then we can use that to fill out the rest of the table. So now if I want to continue on any one of these lines, say, I know that F of 4, 3 is 215. So if I want to calculate F of 6, 3, I want to calculate F of 6, 3. I just need to add 40 to the 215. I'll take the 215 at 4 and add 40. And once we have the pattern, we can just keep following the pattern. So 255, 295, 335. Any questions?
Professor,
Yes.
I think you forgot to mention that you could do the same with not just add 40, you could also add 90 from X6 Y1, and it'll be the same result.
So we have the change in the Y direction. We have the change in the X direction. They should match up. So notice that if we start off on the X equals 6 row from 165, if we add 45, we'll be at 210. And then if we add 45 again, that lands us at the 255. So we're still adding 45 in the Y direction. And since we add 45 twice, we're just add 90. So increasing by 45 when Y increases by 1 is the same as Z increasing by 90 when Y increases by 2, since we have a linear function. So we can also say 165 plus 45 twice. Any questions? So we've got lots of different points, and we have two different directions. Since z increases by 45 when y increases by 1, we can write that the change in z with respect to y is equal to 45 over 1. So we have two slopes now. The change in z with respect to y is equal to 45 over 1, or 45. And the change in z with respect to x will be 20. So delta z over delta x is 40 over 2, which we can simplify since we have a linear function and our rates of change will be constants. We can simplify that to 20. 40 over 2 is 20. So now I've got a rate of change in the y direction and a rate of change in the z direction. So now I can write the equation of a line. I can pick any point to start. So I can choose x naught, y naught, and z naught. I'm going to choose this point to be when x is 2, y is 1, z is 85. And I can write my equation the same way I wrote the equation in the x and y example. So I'll say z starts off at 85 and increases by 20 in the x direction. So that'll be x minus 2. And increases by 45 in the y direction. So plus 45 times y minus 1. It's the same thinking that we applied in the two-dimensional case. So the equation demonstrates that same thinking. Z is 85 when x is 2 and y is 1. Z increases by 20 when x increases by 1. And z increases by 45 when y increases by 1. That's what this equation is telling us. Here we have the equation in some sort of point slope form. We could figure out what's going on at the origin by multiplying all this out. So if we want a more y equals mx plus b format, we can just simplify all this stuff. I'm going to box this one up because this one is just as good as any other. In fact, it's better because in this particular problem, there's no context, but what if 0, 0 just doesn't mean anything in this problem? Then why are we writing y equals mx plus b? We don't care what's going on at 0. So this is a variation of the point slope equation. And if we multiply everything out, 85 plus 20x, notice that the coefficients of x and y aren't going to change. We're just going to shift everything back to 0, 0. Notice that we're going to take the 85 and we're going to take 2 steps back in the x direction. So we'll subtract 40. And then we'll take a couple steps back in the y direction, 1 step back in the y direction. So we'll have the 45. So 80 and 40 and 45, how much is that? 80 minus 45, 85 minus 45 is 40 minus 40 is 0. So we have it in kind of our point slope form. And this is like our slope intercept form. So there's another form that we also see running around called the standard form. That's when we have ax plus by equals some constant c. So ax plus by equals c. For equations, linear equations in 3 variables, we'll just have ax plus by plus cz equals some constants. So in this case, we could write a standard form. Although, since we usually write x first, we don't like if we don't like the coefficient of x to be negative, we could say 20x plus 45y minus z is equal to 0. And then we can have some kind of standard form. So the one to use to express your idea is the one that's going to express your idea the best. So as far as determining which one to use at any given moment, I'm just going to give my most common answer. You'll just know. So how do you know which one to use? You'll just know. If the idea is to just write down your equation, the one that has the fewest calculations is probably best. I know we've been programmed with this y equals mx plus b mentality, but it might not be useful to know what's going on at the origin, because that might not mean anything in terms of the problem that you're doing. So it all depends on what you want to do with the equation, what you're trying to express. And there's a lot of situations in math where that's the situation. No, that's a terrible sentence. Where that's the big idea. You'll just know. And the only way to get there is to gain experience. Like if you think in terms of exponential functions, and if you tell people that the number of zombies is doubling every week, they might freak out a little bit. But if you tell them the number of zombies is increasing by 9% per day, they might not feel so bad, because they're like, oh, it's only 9%. But then all the mathematicians like, oh man, that means it's going to double in a week. So it depends on the level of mathematical knowledge and experience of your audience and what you want to try to convey. If you want to try to convey panic, double every week. If you want to try to convey calm, 9% every day. Or is it 8%? I'm not even sure. But if you use a number like a small little number like 9%, people will go, oh, that's such a small amount. You know what I mean? But this is mostly because people just don't really understand how multiplication works or how percents work. Even though it's like literally in the name, percent, per 100, divide by 100. That's right. You don't have to outrun the monsters. You just have to outrun your friends. Any questions?
Professor.
Yes.
I think there was a case in a video. I think it was from a video game, and they talked about some sort of stats, and they said the crime rate has increased 300%, but it actually didn't increase much. That's actually an example of what you were talking about.
Yeah, that's another thing too, is you want to say something has increased. When you really want to scare people about an increase, you can talk about it's like 100% increase in the number of things that are happening. But if it went from 1 to 2, that's 100% increase. Going from 1 to 2, that's 100% increase. So let's suppose that in the United States in July, we had just 1 murder. I know that's ridiculous for the United States, because we're going to have that, like a couple minutes ago. And then in August, we had 3 murders. If we want to scare people, we're going to say that the number of murders has increased by 200%, and people are going to freak out. But it doesn't mean anything unless we have some baseline information about how many that is. And if it goes from 1 to 3, even though that's a 200% increase, that might not mean very much. Does that make sense? There was a time in this class where the number of students enrolled in this class increased by 200% because there was 1 student and then there were 3 students. And this happened in the matter of minutes. But it went from 1 to 3. So once again, people don't understand what percent means, and people don't know the difference between how much of an increase there is and what that means for as say per population, per 1,000, per million. Any questions? Comments? And here math teachers come along and try to fix it. Well, here's what these things mean. And people are like, oh, when am I ever going to use this in real life? I go, well, you might not be using this in your real life, but I assure you, people will be using it against you. Your lack of knowledge of math will be used against you. I want you to be able to defend yourself. You know what I mean? All right. We need to think about the graphs of what's of these kinds of functions. So now notice that I'm using just a 2-dimensional. This is mostly 2-dimensional. I can't really write on the edge of the paper. So, and it's not paper, it's like plastic. I can't really write on the edge of this plastic. It's too thin. But technically, actually, this piece of paper is 3-dimensional. But there are only 2 dimensions that I can actually use, so it's effectively 2-dimensional. It's one of those situations like, well, actually, dude, is wrong because you know what I was talking about. Actually, dude, so shut it. So we got to think about the ways that we can picture 2-dimensional surfaces in 3-dimensional space and represent them on a 2-dimensional surface. And one of the ways that we can look at do that is with contour diagrams. One of the things that we know is that our equation z equals 20x plus 45y is a plane in a 2-dimensional plane in 3-dimensional space. It's a 2-dimensional surface in 3-dimensional space, and it is in fact a plane. So it's a plane in R3. Plane is significant because plane is a flat 2-dimensional surface. One way that we can analyze a surface in R3 is by looking at contour diagrams or level curves. We can also think about topographical maps. If you're familiar with reading topographical maps. If you play Red Dead Redemption, that's what all those squiggly lines are on your mini map. Those are showing you, that's a contour diagram of the surface that you're riding over. So it's really important to be able to read level curves so that if you're riding from one point to another point, you're not just following the roads, you'll see what a cliff looks like, and you don't try to ride over that. All right, what are we talking about? Oh, yes. So here we have a plane in R3. So what we're going to do for a contour diagram is we're going to draw level curves. We're going to fix values of Z and see what they look like looking top down onto the XY plane. So we're going to look top down . And we're going to draw curves for fixed values of Z. Draw a curve for a fixed value of Z. Notice that when we pick a value for Z and put it into the equation, we get an equation in X and Y. So if we choose a fixed value of Z, if we choose a value for Z, we'll get an equation in X and Y. So for example, let's say Z is equal to 100. We get this equation. 20x plus 45y is equal to 100. And now I knew I was going to regret that 45 instead of making it 50, but oh well. Once we have a fixed value of Z, we get an equation in X and Y. And so if we want to go and draw that, we're just drawing a line. So we're looking top down on the surface. Let's see, when Y is 0, X is going to be, so when Y is 0, or when Y is 0, X is going to be 5. So if X is 5, Y is 0, Z will be 100. And if X is 0, Y is equal to 100 over 45. So when, let's put that here. So when X is 0, Y is 100 over 45. And Z is still 100. So everything along this line Z is 100 on all along this line. Now, if I pick a different value of Z, I get a different linear equation in X and Y. So 20x plus 45y is equal to 50. So I'll get a different set of points. So when y is 0, x is going to be 50 over 20 or 2.5. And when x is 0, y is 50 over 45. So we're going to get this line when z is equal to 50. Notice that every time I choose a constant value for z, I'm going to have the same coefficients of x and y. And so what we're getting, the contour diagram for a plane will be a bunch of parallel lines. So if I pick z is equal to 150, then I'll get another parallel line. Z is equal to 200. When z is equal to 0, we know that that will go through the origin. We found that out earlier. Don't know why I didn't use that information, but and so even though we're looking at all these parallel lines, each of these lines has a different z value. So we can see z equals 0 on this line, then 50, and then 100. So if we go in this direction, we can see that we are going uphill. The values of z are increasing. If we walk along the x direction, if we pick a fixed value of y and walk in the x direction, we can see z increasing by 20 every time x increases by 1. If we pick a fixed value of x and walk in the y direction, we can see z increasing by 45 whenever y increases by 1. So I want to think of these contour diagrams as just topographical maps. We're looking at a top-down, two-dimensional map, but the curves on the map are telling us where the different values of z are. So that's how we can represent the height at any point, x and y. Any questions? Of course, there won't be any questions. There's only 2 minutes left before in the class, so no one's going to have any questions now. Most certainly not the dreaded, is there any homework question? Because students always get mad at the one student that's like, is there any homework? As if the students don't invoke homework, I can't assign it. I'm like, oh, no, that's not true. I have the internet. I can send out an email. It's like, oh, by the way, there's homework. You know what I mean? And ultimately, you should want to do homework. If you're like, oh, well, I don't want to do any homework, then why are you even in school, man? The whole point is to like do work and learn stuff. You know what I mean? I think too often, and I don't blame students for being this way. I think it's just kind of the way we set things up. A lot of students have gotten the message that all you're supposed to do is sit there and absorb knowledge that I dump onto you. And it's just that's not how it works. This is like a thing that you have to participate in so that you can get better at it. You know what I mean? And then students are like, oh, well, why do I have to get better at this? And my usual response is like, well, I don't know, you hired me. Why do you want to get better at this? And then it's always because someone said I had to. It's like, well, no, you don't have to do any of this. If this is like terrible, then go do something else. You know what I mean? I think we get that because it gets, when we're children, we're told things. This is the big crime. We tell children these things. Children are more vulnerable to things like authority because, you know, children don't have a lot of control over their own lives. So they're more vulnerable to being told things that they have to do. And so we spend all of high school just trying to make you compliant. And then you get into college and your professor's like, oh, take a moment and think about this. And you're like, oh, no, I came from high school. I was trained. You're going to tell me what to think about. So what am I supposed to think? You know what I mean? I think the most, like if high schools were like listing the qualities that they had in students, there's like the list that they would like publish, would tell other people like in a mission statement or something like that. And then there's what they really want. And I would be willing to bet that if you let me read minds of high school collectives everywhere, I'm not allowed to, so I have to turn that off. But if you let me read minds, I think the number one thing that a high school wants from a student is compliance. They want you to be quiet and not cause any problems. You do that, we'll get you through this. You know what I mean? So I don't think we should be all that surprised when students go off to college and they panic a little bit when a teacher like looks at them and says, well, what do you think of this? I'm not surprised when I say, well, what do you think? What do you all think of this? And you say, I don't know. What do we all think of this? You know what I mean? I can't teach you how to think. That's just literally impossible. I can just give you opportunities to do it. That's what I've always thought. Anyway, all right. So continue working on the chapter 12 homework. There are 6 sections in chapter 12. Start taking a look when you're looking at problems and you're reading the sections. Start trying to figure out which sections are things that you're supposed to do, like skills that you're supposed to have, and which are ideas that you're supposed to think about. There's a couple of different kinds of problems. That's one big way to classify problems. Is this a thinking thing or is this a doing thing? If it's a doing thing, then I just have to figure out how to do things and practice. If it's a thinking thing, I got to make sure that while I'm doing all that practice, I'm thinking about the thing I'm supposed to think about. If you're ever concerned about what you're supposed to be thinking about, and you can't see what you're supposed to be thinking about, that's a great question to ask me. I can also show you how to do problems, but that just makes me do an example, and it's probably in the book anyway. But I understand reading a math book is really weird. You know what I mean? All right. Oh, I'm still recording. All right. That's going to do it for today. Keep working on your chapter 12 homework. We'll pick up with more stuff on functions of 2 variables on tomorrow. That's it for today. Everybody have a good day. Stick around if you have additional questions. I know I got a couple of messages that you have additional questions, so stick around for that. That's it for today. I'll see you all tomorrow, and thanks for playing.